Hey everybody, and apologies for the delay. I'm really, yeah, it was just a debacle on Wednesday night. First of all, dropping out, Zoom dropped a couple of people out, and then it didn't register the record. So I am re-recording, which is actually a good thing because I was not in a good brain space on Wednesday, as people will attest to, and possibly confused them more than anything. So basically, we spoke about binary code. And we suggested that binary code is something that you actually start with your basic decimal system, which is a base 10 system. And I'm not sure how strong your numeracy skills are yet. Most of you probably did some maths at school, and you've got some idea about base 10 systems. But we've got 10 to the power of 0, which is your ones column, 10 to the power of 1, which is your tens column, 10 to the power of 2, which is your hundreds column, and so on. And of course, when you count with your decimal numbers, what happens is that you count your ones up until the point where you overflow into the tens column, which means you can't have any more than 9 in this column before you overflow, and we'll get onto that a bit later. Now, in the binary system, we have a base 2. So it's exactly the same as the decimal system, except it's a base 2 now, which means 2 to the power of 0 is 1. 2 to the power of 1 is 2, 2 to the power of 2 is 4, and you'll notice that 2 is a very convenient number because effectively, without having to calculate 2 times 2 times 2, 2 times 2 times 2 times 2, of course you multiply by an extra 2 at the end of each multiplication, which means effectively that you double all the way up. Now, I've got 8 pieces of information here, deliberately so, but you can go upwards as far as you want to go. And we certainly do go upwards as far as we want to go. When I explain to you about the way that the system works, you'll understand that a bit better. So that is the base 2 number system, which we call binary code. Now, why is this important? It's important for this reason. If I move onwards, basically, if I have the base 10 system, I can have up to 9, yeah, in here and so forth, so that I can move upwards and upwards and upwards. But with the base 2 system, obviously, the maximum I can have in this column is a 1. So I can't have any more than a 1, because if I have an extra 1, I go up to 2. I can't have more than one lot of 2 here, because if I double my number of 2s, I get up to 4. So we can only have 1, 2 in this little holder there. If I have 4s, I can't have an extra 4 because if I add an extra 4, I get up to 8. And I have to overflow into the next column. If I have 8 here, I can't have another 8 because I could only have 1 8 because 2 8s will take me up to that column. So it means you could only have one or none, of course, one or none of each of these values in each column. So this might have no 8s or whatever, in which case you put in a 0. This might have no 2s, in which case you put in a 0. And that gives you your binary number. What does that mean in terms of computer science? What it means is that you have either a 0 or a 1 in each of these placeholders, and that will tell the computer to open up a gate or open up a circuit or close down that leg of the circuit, which is called closing the gate. So if there's a 1 in that column, the computer reads that and says, open that part of the system, in other words, turn the switch on. If there's a 0 in that placeholder, the computer knows that this particular switch is turned off. And so you've got, obviously, thousands upon thousands upon thousands of different little routes in your computer, and your computer knows exactly what to turn on and what to turn off, which goes through to the components, which then gives it capacity to work for you. So that's why binary code is such a fantastic way of working with your computer. So if we go into, and let's stop with 76, that's a hard one. Let's basically go to 5. And convert that to binary, and let's get rid of all of this. Okay, so basically if I've got 5, I can start working with the lowest number, but generally when you do division, don't you work with the highest possible number? So if I start with 5, obviously I've got a 4 in there with a remainder of 1. I don't have an 8 in there because that's too big, so I can go to my largest number that will actually subtract from 5, and that's 4, and that means I've certainly got one group of 4 in that binary number. Now my remainder when I take 4 away from 5 is 1. I don't have enough to have a group of 2. I only have enough to have a group of 1. So your binary number for 5 is, in this particular case, 000000101. It's pretty easy. So let's change and let's go to, let's say 11. Okay, so I'll change that back to 0 so we can start again. And I'll change that back to 0 so we can start again. Now, 11, basically what is the largest number within these groups of numbers that we can take away from 11? 16 is too big, 8 is small enough. So we'll take 8 away from 11, which means that we actually have one group of 8. What have I got left over? 8, counting on my fingers, 9, 10, 11. I've got 3 left over. I don't have enough to make a group of 4. I do have enough to make a group of 2. And I have 1 over, so that gives me a group of 1. So the binary code for 11 is 00001011. Now, the video that I've got on the Moodle site also works on counting in binary, which is quite easy. And I'll just do this orally. So let's go back and just ignore these zeros. If I have 1, I'll have a 1 in this column. If I have a 2, I'll have no 1s. I'll only have 1, 2. If I have so, I'll have 1, 2. If I have 3, I'll have one lot of 2, and I'll have 1, 1. So the binary number for 3 would be 00000011. If I have 4, I've got enough to have a whole group of 4, but I won't have any 2s left over, and I won't have any 1s left over. So you can see you keep moving leftwards as you go, subtracting everything on the right hand side and then adding it back in again to count upwards. If I have, for instance, 17, okay, going up there, I've got 16 that I can fit in, so I've got 1 there, and then basically I've got to count up to 17, and that means I've got 1 there to count up to 17. So starting to play with counting numbers certainly gives you a better sense of what binary numbers are and give you a sense of how they work. So let's go to this one over here then. We want to convert 76 to binary. Okay, so going upwards, 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 the biggest number that we can take from 76 is 64. So I subtract 64 from 76 and I have a remainder of 12. That means I must have one group at least of, well, only one group of 64s. Now what do I do with that 12? 32 is too big, 16 is too big, 8. I can take 8 from 12, so I'll take out a group of 8. That leaves me 4 over. I can take a whole group of 4 out, and that leaves me nothing. So basically my binary number for 76 is 01001100. Finally, if I want to go up to 132, exactly the same thing. I can subtract 128 from 132. Now, if I need more, I can certainly add another box up on the left there and put on 256. I can go upwards and say 1012. So I can keep going leftwards by doubling my numbers all the way through. But at the moment, I've got enough here to work with. So subtracting 128 from 132 gives me one group of 128 and a remainder of 4. I've got nothing all the way through here until I get to the 4s. I've got one group of 4 and I've got nothing over. So that is my binary number for 132. Working backwards, converting binary to decimals is just as easy as doing a multiplication. So if I've got this number over here, I'd better put it in. So basically I would have 1 there and 0 there, 1 there, 0, 1, 1 and 0. Which tells me, if I just get rid of that, okay, which tells me basically that I have got one group of 64, so I'll have 64, and I will have one group of 32, so we'll add that on. I've got one group of 8, I'll add that on, and I've got one group of 2. And when I work that out, that will give me the decimal number for 64. For 1101010. Okay, so those are your binary numbers. Now I want to point out something little to you. If I go and I take 8 binary numbers, one binary number is a bit. So I've got 1 bit, 2 bits, 3 bits, 4 bits, 5, 6, 7, 8 bits. If I take 4 bits together, that's actually called a nibble. And if you wondered what a byte was, now you know, because 8 bits make a byte. And that's why I've been working all the way through with bytes of information, because generally you'll work with bytes. Now, what is the maximum value a byte can take? Let's work through. It can have 128 plus 64 plus 32 plus 16 plus 8 plus 4 plus 2 plus 1. You can have a maximum value of 255. Keep that number in the back of your mind. And then let's move on to color. I'm going to put in a little bit of text, a text box. Hang on, I'll put in another text box. Don't want it there. There. Okay. And I'm going to do what we were doing in our little unit, and that's talking about fill colors. And I'm going to work with these fill colors. Now, these numbers over here tell you exactly how much red you're going to have, how much green you're going to have, and how much blue you're going to have to give that color. And at the moment it's 91, 155 and 213. I wonder what the minimum is. Let's go all the way down, and obviously the minimum is no red. So this color now only has green and blue in it. If I go upwards, I wonder what the maximum red there is. Counting up, 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 up. 255. Gee, that makes sense. Let me go back again to the slide and think about the totals here. 255, that would give us a byte of information. In other words, to code for each one of these colors, you would actually use a byte of information. That is 3 bytes. And those numbers in combination will give you your actual number. So that's the way you play with colors when you play with colors in binary. So basically, if I was telling my computer that I want to color this particular little patch of the computer screen, and let's call that patch of the computer screen a pixel. If I want to color that pixel exactly that color, I'll tell the computer to have 255 in terms of the value of a byte of information. Now I'll have to convert that, so that will be in computer talk 1111111. If I take this down to, let's say, just go down to a little number so it's easier to work with. Come on, Wendy. Okay, let's say I want 9 as my value for green. Basically, when I come to my binary code, I will have to have 1, 0, 0, 1. So my binary code for 9 is 00001001, and that's what I'll tell my computer. I actually want that for that color. And the same with 213, and I'm not going to do that calculation, but basically that would be a binary number for 213, and of course the maximum it can be is 255. If I have a maximum of all my colors, I wonder, let's type it in. 255, 255. And that gives you white. And of course you know that white light is a combination of all of the colors of the light together, and it's split into the rainbow. Fortunately for us, red, green and blue will actually mix to give us all of the colors that we've got here on the color wheel. So there you go. That's the way that color is determined in your computer through computing. It's a byte of information for each color. That's 3 bytes. Now let's look at the value of these bytes. We use the power of 10, so basically a kilobyte is 2 to the power of 10 bytes, which is 2 times 2 times 2 times 2, 10 times, which is 1024 bytes. We're all used to the decimal system, so we all sort of talk to ourselves about it being approximately 1,000. And it's, yeah, you know, but it's more accurate to say 1024. And you've probably seen this when you've looked at the value of flash drives and hard drives and so forth. A megabyte is 2 to the power of 10 kilobytes. That is 1024 kilobytes, or 2 to the power of 20. So we double that value. 2 to the power of 20 bytes, which is 1,048,576 bytes. And you can see it just going up exponentially as you go. A gigabyte is 2 to the power of 10 megabytes, or 1,024 megabytes, which is, look at that big number, I'm not even going to read that to you. It's a lot of bytes. So basically it adds up fairly quickly, and we have to be a little bit careful about the way we use them. So if we go and have a look at data now, just to give you a sense of how much a byte is. Okay, starting off, sorry, I've lost my slide. There you go. There is. So a byte is 1 character of text. And so every character of text would have to have 8 values in that byte. And you can look that up if you wish and play with that. So just search for binary code letters and you'll find them. A number also is 1 character of text. A comma is a byte. A comma is a byte of information. So every character is a byte. So there'll be 8 little values in sequence to give you that byte of information. A kilobyte gives you about 2 to 3 paragraphs of text. A megabyte is about 200 pages, which is 240,000 characters of a book, or 873 pages of plain text. In other words, the more you format your text, the more expensive it becomes in terms of file size. So less formatting is better formatting. Okay, now, in the good old days and even now, uploading a megabyte can be time-consuming given Australia's broadband speed. It's not very broad at all. But you really don't want to upload anything that's too big. So if you have file sizes that are too big or you have pictures that are too big, you're simply going to choke the pipeline and you won't be able to upload them, and everything in your computer is going to wait because you can't upload stuff to the web. So it's important to consider how big these file sizes are. Incidentally, your upload speed is a lot slower than your download speed. That's the way that it's configured with your internet service provider, because they assume that people don't upload. It's interesting how the world has changed and that we do upload, and they haven't adjusted for that. But if you upload stuff to the web, again, if I have anything bigger than, for instance, a 2 meg file, it's going to take a bit of time on my internet speed and possibly yours as well. So that's something you need to consider. And one of the reasons why your files didn't upload to Weebly when you had your images and you tried to upload them simply is that the file is too big and it just won't upload, it stalls. One of the ways to get a really big file is to go into PowerPoint and put in lots and lots of high resolution images, and it'll take forever for that file to upload. So be aware of that as well. Audio files, look at this, 4,000 books compared to 256, quite big, 4 meg audio files. And that explains why the audio quality of the feedback I gave you on your assignment was not wonderful, because I downsized it because I didn't need to have it sound pretty. I just needed you to be able to hear the sound. So basically I downsized it as far as possible so that it was functional, but it uploaded and downloaded quickly. Now, in terms of colors, let's go back again and do a calculation. So, we have patches on the computer called pixels, and each pixel takes 3 colors, so 3 bytes of information. I have a photograph. It's got a resolution of 800, that should be a size actually, not a resolution. So it's got a size of 800 by 600 pixels. That means it's got 800 across the side and 600 up the other side, which is 480,000 pixels. How many bytes would that be? Well, if I multiply that by 3 bytes, I get 1,440,000 bytes. So basically, I've got a file size of about 1,406 kilobytes. And that's getting up. That's about 1.3 meg. So even though it's quite a small size, now when we think about screen size, an average older screen is about 800 by 600. The big wide screens you get, like the 22-inch monitors, can hold more pixels, of course. But you wouldn't want to put an image that into a web page bigger than 800 by 600 because it'll fill the screen, and for some people it'll actually overflow the screen, so they have to start scrolling up and down to see the rest of the picture. So uploading that is about 1.3 meg, and that's going to be somewhat problematic. But when we look at the little orange I used last week, that was 225 by 225 pixels, which should actually be quite a lot of kilobytes. But the file size was only 6 kilobytes, and I made it as small as possible. And you just wonder, how is that possible? So the other thing that probably is useful to understand, when you're doing your resizing and you're playing with images, Paint doesn't do it, but other programs like Photoshop and GIMP do, your image size also depends on the number of colors per pixel. So if I go down here and have a look, this is 24-bit bytes per pixel. That's 3 bytes. 3 lots of 8 bytes, there it is, gives you that many colors. Basically, sorry, bits per pixel, that's why I'm getting confused. 24 bits per pixel is 3 lots of 8 bytes per pixel. So that is what we're looking at when we look at our RGB colors, which is a heck of a lot of colors for your computer to remember, and basically that increases the file size hugely. If I say, look, I don't need that sort of nuanced color, I can get rid of some of the shades of color, I can start going down, 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 down. And if you think about the little orange we had, really it was 2 colors. It was orange and it was green. So 2 colors would do that, which is 1 bit per pixel. And that is hugely smaller than 24 bits per pixel, which basically gives me a much, much, much smaller file size. So there are 2 ways you can play with file size with images. The first way is to actually just play around with the number of pixels you've got, and that is the activity you've done this week. And the second one basically is to play with the colors.